As an example, let's consider straight-wall diffusers. As you probably know, a diffuser is any passage that decelerates the flow and causes a rise in pressure. In subsonic flow, the diffuser is merely a diverging passage. Between 1900 and about 1950, a number of studies showed that if we increase the divergence angle of the diffuser, 2 theta, that the pressure rise is increased up to some modest angle. But further increases in angle cause the pressure rise to decrease. At that time, we still did not have, however, any good picture of the overall flow patterns, nor did we have good methods for predicting optimum performance. We then began a series of systematic visual studies, and these quickly led to better understanding and to improved predictive methods. The bubble technique can show us what these patterns actually are. Let's start with the walls parallel. Notice how the velocity drops sharply near the wall, and in this region the particles slide evenly over each other. This low velocity region is called a laminar boundary layer. Now let's open up the diffuser to a total angle of about 7 degrees. The increasing area of the passage causes the velocity to decrease and the pressure to rise in the direction of flow. Watch a streak square in the middle of the passage. You can see the deceleration. Also notice the flow near the wall. You see a thicker boundary layer now, and it is no longer steady. Instead, you see irregular, time-dependent eddies. This kind of boundary layer is called turbulent. Even though some of the particles very near the wall do not have enough momentum to overcome the rising pressure, they mix with the particles farther from the wall and are given sufficient momentum to keep moving in the downstream direction. If we increase the divergence angle of the diffuser further, something new occurs. Slow-moving particles begin to accumulate near one wall and then move upstream, forming what we call a stall. The mainstream is forced to separate from the wall and move around the stall. The pressure change caused by the movement of the mainstream is enough so that after a short time the stall washes out again. The whole cycle of stall buildup and washout then repeats in time. These unsteady motions we call large transitory stall. In this regime, the whole passage acts like an oscillator, even though the upstream flow is steady and symmetric. If we increase the divergence angle of the diffuser still further, the stall forms a relatively steady recirculating region on one wall. The mainstream separates very near the throat and hugs the other wall. If we move the mainstream to the opposite wall, it stays there. The pattern is what we call bistable. Usually we refer to this pattern as fully developed stall. If we increase the diffuser angle to high values, the flow separates from both walls. We observe a jet flow pattern. In studying fluid patterns, it's important to examine the whole flow field. Here's a diffuser with a lower divergence angle. A bubble wire near the surface of the flow shows an entirely unstalled flow pattern. But now we'll turn off this wire near the surface and turn on another one deep in the flow near the floor of the channel. This wire shows us that one corner of the flow contains a large stalled area. The wire near the surface still shows unstalled flow. If we'd used this wire alone, it would seriously have misled us about the nature of the flow pattern. Like any other experimental tool, flow visualization must be used with care to obtain reliable results. Knowledge about flow patterns is most useful when it's summarized in the form of a correlation. In the case of our diffuser problem, we can show the summary by this chart. It shows divergence angle 2 theta plotted versus length to width ratio, the length of the diffuser divided by the width, N over W. The chart shows us when we will find each of the 4 flow regimes you've seen in terms of the parameters. These lines indicate shifts from one flow regime to another. One point that needs emphasis about these shifts in flow regime is that it's very seldom that we can predict them on theoretical grounds alone. Even when we have a good flow model and a sound theory based on it, within a given regime, we may not be able to predict where that regime ends. This is the case in the lowest region. In this region, if we stay well below the line of first stall, then we can use Prandtl's potential theory boundary layer model to make accurate predictions about the flow and about performance. But there is presently available no theory that will predict the transition, that is, this whole line. Higher up on the chart, in the other regions, the theories are not as complete, and there is no theory that will predict this line or the hysteresis region either. We might summarize all this as follows. When we first begin to study a problem in fluid mechanics, we may not even know the gross flow patterns to expect. After we've accumulated enough systematic information, in visual form or by other means, we can correlate the data, as for example on the chart. Finally, we can use the flow models so found as the basis for mathematical models, and if these are successful, we can then make paper and pencil predictions about a good many details. We can do that in this regime on the diffuser chart. The information inherent in the second or correlation stage is often useful for other purposes. Sometimes it tells us how to locate optimums, and sometimes it suggests improved designs. In the diffuser example, the lowest line, in fact, tells us the geometries that give maximum pressure rise for a fixed length of diffuser. The chart itself also suggests a way to improve short diffusers. Short diffusers usually mean wide angles, but wide angles mean separation, poor patterns, and poor performance. The chart suggests that perhaps what we ought to do is to divide up the passages into smaller passages, each one of which does not cross the first line of stall either this way or this way. Let's see if this idea works.